Passenger planes actually did carry parachutes once. For a brief window around 1930, early U.S. aviation rules included a parachute supplement. And it made sense at the time because planes were slow, flew low, and bailing out was genuinely survivable. Then aircraft got bigger, faster, and pressurized, and the whole calculus changed. So the real question isn't why did nobody ever think of this? They did. The question is why it became physically impossible, and the answer is a lot more specific than most people realize. This video is going to walk through the actual engineering reasons parachutes don't work on airliners, the one case where a whole plane parachute system does work, and the genuinely strange real-world data points that prove exactly where the limits are. By the end, you'll have a much cleaner picture of what would actually have to be true for this to work, and why none of those things are true on a 737 at 35,000 feet. Let's start with the one place parachutes do work on aircraft, because it completely reframes the conversation. Cirrus Aircraft's whole airframe parachute system, called CAPS, has saved more than 280 lives since its introduction in 1998. It's FAA certified, it's standard equipment on every Cirrus they build, and it works by firing a rocket that pulls a large parachute out of the fuselage, lowering the entire aircraft, not just the people, to the ground. One handle pull, the whole plane floats down. As of July 2026, there have been 150 saves with 302 survivors in aircraft equipped with the system. That's not a hypothetical safety feature. It's a proven one with a real track record. So why isn't that on a Boeing 737? The answer comes down to a very specific engineering ceiling that Cirrus's own system makes obvious. The system must be activated at airspeeds less than the aircraft's published parachute deployment speed, which ranges by model from 135 to 140 knots indicated airspeed. A commercial airliner cruises at around 450 knots. Standard parachute canopies are engineered to open at roughly 110 knots. Deploy one at cruise speed, and the fabric shreds instantly. It's not a design flaw, it's just physics. The forces involved are so far outside the operating range that no canopy material we have could handle it. And the Cirrus aircraft that CAPS works on weighs roughly 1 metric ton. A wide-body airliner weighs 200 to 300 times that. Scaling a parachute system from a car-sized aircraft to something that heavy isn't an engineering challenge. It's a different category of problem entirely, and one that doesn't have a solution within the laws of physics as they currently exist. This is also why fighter pilots don't just jump out of their jets when something goes wrong. As aircraft got faster, the backpack parachute evolved into the ejection seat. Because a human body can't survive leaping unaided out of a fast jet, the airspeed alone would kill you. You need a rocket to physically throw you clear of the airframe before the parachute even becomes relevant. And that's a single seat for one trained person in a military aircraft specifically designed around that system. Scaling that idea to 200 passengers on a commercial flight is a completely different proposition. Now, let's say you accept all of that and still want to try. Here's where the math gets brutal. The doors on a pressurized airliner at cruise altitude physically cannot be opened. And it's not because of a lock, it's because of pressure. At cruising altitude, the cabin is pressurized to a comfortable level while the outside air is extremely thin. That pressure difference pushes the door into its frame with a force equivalent to several tons. These are plug doors designed specifically so the pressure itself seals them shut. There's no handle strong enough to overcome that. The door isn't locked, it's being held closed by the atmosphere. Even if you solved that, you'd still have the altitude problem. A commercial airliner cruises at around 21,000 feet or higher, and at that altitude the air is too thin to breathe without supplemental oxygen, and the temperature outside is 40 to 50 degrees below freezing. A person jumping out in a normal winter coat would lose consciousness within seconds and be dead from hypothermia before they got anywhere near the ground. You'd need a full pressure suit, an oxygen supply, and specialized cold weather gear for every single passenger. That's not a parachute problem. That's a completely different system layered on top of it. Then there's the timing issue, and this one is the most concrete. Recreational skydivers maintain roughly 500 feet of separation between successive jumpers, several seconds between each person exiting the aircraft. Take a plane with 200 passengers, 1 or 2 usable exits, and that spacing requirement, and do the math. You'd need somewhere around 15 to 20 minutes just to get everyone out, assuming perfect execution, no panic, and every single person already trained and geared up. Most emergencies that would require this happen fast. The plane would be on the ground, one way or another, long before half the cabin made it to the door, and most crashes don't happen at cruise altitude anyway. The takeoff and landing phases, which happen at low altitude, account for a disproportionate share of accidents. At a few hundred feet off the ground, a parachute doesn't have enough vertical distance to fully deploy before you hit the ground. The one scenario where parachutes would theoretically be most useful, a catastrophic failure at altitude, is also the one where every other variable works against you. Here's the part that most people don't expect. There's real data on what happens to a human body falling from airliner-relevant altitudes with no parachute at all. On Christmas Eve 1971, LANSA Flight 508 was struck by lightning and broke apart midair. 17-year-old Juliane Koepcke fell about 10,000 feet, still strapped into her plane seat, into the dense Amazon jungle. At some point she lost consciousness during the fall, but miraculously survived the impact, waking up amid the wreckage as the only survivor out of 92 people. Several factors contributed. She remained strapped to her seat, with the adjacent seats slowing her fall, and windy updrafts along with the rainforest's dense foliage are thought to have cushioned the impact. She's not the only case. A Serbian flight attendant named Vesna Vulovic survived the world's longest-known fall from a plane without a parachute just 1 year later. A mid-air explosion in 1972 sent her plummeting 9 kilometers into thick snow in Czechoslovakia. These aren't arguments that falling from altitude is safe. 91 other people on Koepcke's flight didn't survive, but they are evidence that the physics of deceleration, tumbling debris, and dense landing surfaces can do things that seem impossible. Now here's the one time someone actually did parachute out of a commercial passenger jet. And the conditions required to make it work tell you everything. On November 24, 1971, a man named Dan Cooper boarded a flight from Portland, Oregon to Seattle. He's known to history as D.B. Cooper. After collecting a ransom of $200,000 and 4 parachutes in Seattle, he directed the crew to fly to Mexico, and somewhere over southwest Washington lowered the plane's tail stairway and vanished into the rainy night. The 727 was flying just under 10,000 feet at a speed of around 200 knots, conditions Cooper specifically demanded. He needed the plane slow, low, and unpressurized to make the jump survivable at all. Even then, he parachuted into a thunderstorm with winds in excess of 100 miles per hour and temperatures well below zero. The FBI has generally maintained that his jump into the freezing sleet over a thickly wooded area was fatal. Nobody ever found him. The ransom money was never recovered, and the Boeing 727's rear air stair, the specific door design that made the jump physically possible, was quietly modified by the FAA after this incident so it could no longer be opened in flight. That modification is still called the Cooper vane. So here's where all of this lands. Parachutes work on aircraft. Cirrus proved that definitively, over 140 successful deployments, saving 280 or more lives across all Cirrus aircraft models. The system works within a very specific envelope: small aircraft, low speeds, the right altitude. Every one of those conditions is the opposite of what a commercial airliner operates in. The doors can't be opened at altitude. The speed would destroy any canopy. The cold and thin air would incapacitate passengers before they reached the ground. The timing math doesn't work. And even if you solved every single one of those problems, you'd need every passenger trained, equipped, and calm enough to execute a coordinated mass skydive in an emergency. That's not a parachute problem. It's a different mode of transportation entirely. The reason your flight doesn't have parachutes isn't that nobody thought of it. It's that the people who did think of it ran the numbers, and the numbers don't work. The safest thing on that aircraft is the aircraft itself. If you've ever wondered about another aviation mystery, like why planes are actually struck by lightning more often than you'd think, or how fly-by-wire systems changed everything about how modern jets are controlled, those videos are right here. Drop a comment below with the aviation question you've always wanted answered, because a lot of these scripts start with questions from people watching. And if you're not subscribed yet, this is a good time. There's a lot more of this kind of thing coming.